Zurich University of Applied Sciences. I just put your videos here on my other screen so you can see my slides. Yeah, I'm from Switzerland. We have our offices in Winterthur, but at the moment I'm, like most of my colleagues, still in home office. This is why you see a nice picture of our university in my virtual background. You might have known about ZHAW already from another colleague of mine, Rudi Füchslin, who's probably also in the call and who served already at the ECLT in different roles and might be known to some of you. So today's talk is about machine learning based pattern recognition, for example, for document analysis. I will do, oh, I have to go here. I will do basically two things. I will introduce the group and then introduce you to two use cases that we have been working on or are still working on in my group that happen to revolve around document analysis. Actually, in the group, we are agnostic with respect to the use case. What we are doing is really we do pattern recognition, and we do it on, let's say, high dimensional sensory signals, which happen to be images or audio most of the time. So we are dealing with deep learning. Usually this is the tool we are analyzing and researching on, and we do that by working on a lot of different use cases. The agenda of the talk is basically, I will quickly say something about the group. We'll go into two use cases. First, music scanning or optical music recognition. We'll then go to shorter, probably to one on print media monitoring, and then have a quick outlook on what is currently going on, hopefully, or with the intention of maybe you're doing something similar or are interested, and we can get in touch afterwards and maybe start a great initiative together. And I'm really happy, Achil, that you said you will manage the comments and inform me if there are any questions, because I don't think I see the chat at the moment. So I'm happy if you just interrupt me if there's anything. And also timekeeping, I'm happy for that. Thank you. So very quickly about our university. If you don't know it yet, you see here a picture in the bottom left of the building that is my virtual background from the outside. We actually date back to the 1800s, and we had once Albert Einstein as one of our lecturers for just one semester, then he left and did his famous work, but he was there. It's one of the largest, probably the largest multidisciplinary university of applied sciences in Switzerland. And I'm working there at the School of Engineering, which hosts an Institute of Computer Science, and within that focus group on information engineering, within which I have a team on machine learning. So now we have all our hierarchy, which is not so relevant. More relevant is what we are doing. We are doing pattern recognition using machine learning. And when I look at the different cases we have, a couple of themes emerge. One is that we have the case of robustness almost in almost all cases, because almost all of our research projects are together with industrial partners. That might be a very interesting research setting for some of you. For us, it's really the normal thing that we have a partner from industry that has a use case that cannot be solved with anything you can buy on the market. So they come to us and ask if we can do something about it. And usually robustness is really key, because the stuff needs to work later on, so to say, in the field, on the shop floor, in the product. So it needs to be robust against changes in the distribution, robust against misuse, robust in every aspect, basically. And we saw that, for example, in some applications we did for predictive maintenance. But we see it also in medical imaging, where you need robust results. Right? Nobody wants an assistant system to his doctor that is wrong in a certain amount of cases. So robustness is really key, one key aspect in many of the research projects we tackle. Among the emerging themes within the different use cases, we work on voice recognition is one that already goes along with me since my own PhD time. We were one of the first groups who applied deep learning methods to speaker diarization, and have some very interesting results currently that I hope we can publish later this year. Document analysis is something we happen to work on quite a lot. I will not go into detail now because the rest of the talk is on it. And something a little bit unrelated, but there's still a bridge, is not pattern recognition actually, but learning to control something, learning to learn new learning algorithms. Of course, this hints at reinforcement learning, and the bridge is deep learning, which is used in reinforcement learning and in pattern recognition. For us, it's actually a really good opportunity to have a real link, not just a nominal one, to artificial intelligence, because pattern recognition may be a sub area of it, but it only really becomes interesting from an AI point of view when you're not just dealing with a data set, but you can actually steer and control something and have an active feedback loop. I was very happy when two of my students were tackling this in a recent thesis work, where they tried to reboot computer vision by analyzing how we can overcome the paradigm of we only get a fixed data set of single images and we do recognition on a single image. Why can't we put the data acquisition within the analysis loop? Like we have the camera, we get an image, and then we decide where to look next in order to get a better picture and hopefully reduce the uncertainty in our prediction. Very, very interesting. So this learning to learn and learning to control has a definitive link to the pattern recognition work we do elsewhere. That should have given you an overview of what we are up to in the group. You see my collaborators, my employees, PhD students, postdocs to the left here. And I would say let's directly jump into the use cases. And the first one will be what is already hinted here, music scanning. So what's the problem in music scanning and why are we working on it? So the problem actually is you have a piece of written music, musical score. For the sake of simplicity, let's say we have one page of music. And what we want to have in the end is a digitized version of it, and not just a scanned PDF that we can picture on a tablet device, but a version that is digitized in a way that it is machine readable, so the machine actually understands what it is displaying. You can have convenience features like transposing it up and down for a couple of notes. For example, if you want to sing and it's early in the morning, you want to have it a little lower, or you want to jump directly to a specific measure. And of course, all this doesn't work in a PDF file. You need to have some intermediate representation so the music can understand, the machine can understand the music. And this intermediate representation usually is music XML. And our project is about converting scans or digital printed written music into music XML, image-based. So if we just have the image of a picture or something of written music, we want to automatically convert it to music XML so that it can be displayed on a tablet. Why? Because there's a company, I think they now changed their logo to a more modern form. What you see their old logo in the top right, ScorePad. It's a startup from the Zurich area. Their goal is actually to provide such a digital music stand for mainly professional musicians, orchestras and the like. And for them, it's really a relief if they don't have to carry on lots of printed sheets, but have everything with them in digital form. So there's a real business case behind it. We have been working on this project in different settings since 4 years already. So it's already in production, parts of what we are doing. And I'm telling you a little bit of how this yellow arrow here, going from image to music XML, how does it work better than before using deep learning for the object recognition part. Let's go into it. So what's a challenge in detecting musical symbols? So first, it's an object detection setup. So you can basically compare it to other object detection challenges, like what you see in the Pascal VOC or the MS COCO data sets. What you see here is a typical picture from those benchmark data sets where you have rather small image with rather big foreground object that need to be detected and segmented. And to the left, you see a typical image like it enters our system. Of course, they're all shrink to a size that can fit the slide, but it's in proportion. So you see our page is quite a bit larger than the typical object detection benchmark data sets, and we have a lot of more much smaller symbols on them. And that's the reason why you cannot, and I will go into more detail on a couple of slides later, but you cannot just use your famous RCN, YOLO, whatever approach that works very well on these kind of data. It just doesn't work with larger images and so small objects. So that's the first challenge. But there's another one that is specific to the music notation. All of us who learn to play the flute or something as children, at least, probably know this. There are symbols that look exactly alike optically, but change their meaning depending on context. It's probably most obvious with these dots here. The dot over a note means it's a staccato dot. It means the note has to be played very abruptly. And the same appearance of a dot after a note doesn't mean anything of playing it abruptly. It just changes the temporal duration of the note by half of its nominal value. So when we want to detect musical objects on an image, we cannot just identify the object in isolation. We have to identify it in its context. Just a third challenge from the many more challenges that exist in music recognition. You probably cannot read the numbers that are printed here, and it's not so important, but what you see here are all the symbols we can detect with our detector currently, which are basically the 130 most famous musical symbols, most famous in quotes. This is a black notehead. It makes up 55% of all of our whole data set, which is, by the way, the largest up to now annotated, with ground truth annotated object detection data set on the planet. We created an open source set. So the notehead black makes up 55% of all the objects in that huge data set. But already, if you go to the second line here, it's ordered by a number of occurrences. Here it's, I think, the staccato dot. It only appears in 1% of the cases. And for the last 5 or so symbols in the data set, in this huge data set with more than 300 million annotated objects, the symbols occur only a handful of times, literally. So it's a very, very skewed distribution of classes, and it's very hard to achieve a high average precision averaged over all the different classes, meaning objects. So these are a couple of the challenges attached to the optical music recognition problem. And here is the sketch of our solution to it, and I will go into more detail on the following slides. So the idea is, in order to capture the context, we put in the whole high-resolution music sheet at once into our network, deep neural network, which is at its core not very innovative. It builds on a big ResNet, followed by a refine net to refine some of the features. And what is interesting is that after our classifier part, we basically have, there the innovation begins, we have 3 different output heads. So our network, for every input, not just outputs a single thing, it outputs 3 different things, 3 classifications, if you will. And as you can imagine from the shape of the result that is displayed here with these colorful matrices, it's a fully convolutional architecture. So we have 3 different outputs per input pixel. So what are the 3 different outputs? We have a so-called energy level for every pixel that tells, maybe energy is a bad word, it tells the probability of that pixel being the center of an object. Per pixel, we have that probability, or energy, objectness energy, we call it in the corresponding paper. Then, for every pixel that is not based on the first classification of the energy levels considered background, for every pixel that's not considered background, we have an annotation with an estimated class. So we know where are the centers of distinct objects, and we know to which class do they correspond. And for every pixel, we have height and size of a bounding box that could start there. When we combine these, we are completely able to compute from a pixel-wise input like the one you see in the top left, the type and location of every musical object on the page. And this is exactly what our approach does. We get the location and the class of every single musical object. We pass that on to an open source optical music recognition system. And that is doing the conversion to music XML and doing a rule-based improvement of the results on the background. So we don't cope with that translation. We just cope with the pattern recognition of the images. Let's go into some details. First, results. That worked, as we hoped, pretty well on perfectly rendered created PDFs of scores. Our data set is synthetic, so perfectly rendered scores, not yet scanned or something. Much to our surprise, it worked almost equally well on the one handwritten music dataset that is annotated and out there publicly called Musima++. We almost had equally well scores on handwritten music than on the perfectly produced printed scores. So we attribute that to the generalization power of the deep networks, and we're quite surprised that that worked so well. So I promised you to talk about why don't we just use the standard object detectors that are state of the art. Quickly back, YOLO and RCNN that I mentioned here are, or their descendants actually nowadays, are state of the art for object detection like you see here in that natural world images that, just to remind you, are very small with very comparatively large objects in the foreground that should be detected. And that's actually the problem. If you look at YOLO or any other detector of that type, they superimpose a grid on the image and then try generate bounding boxes aligned to the grid and then decide by some process which of the bounding boxes are actually the ones to report. The problem is if your objects are not as big as the dog here or the car or the bicycle, but as tiny as 2 by 2 pixels, the staccato dot, we need to have a very, very fine grid, and that is computationally impossible to do. We did a lot of experiments with YOLO 2 years ago when we first published the results, also with RCNN. It completely didn't work. We did some more experiments this spring, faster hardware, different other tweaks and improvements. It now works so, but still not very good. And it's basically the same with RCNN. You get a prohibitively large amount of region proposals by the network, so that it takes basically forever to compute for a single sheet of input. So these kind of detectors are not very well suited if you have tiny objects and large inputs. Of course, somebody could say we could just put a sliding window over the image and put the sliding window through YOLO or RCN. Yes, we could do that, but then we have to deal with this contextiness of music again in the post-processing, which would make the approach much harder and shift the problem to later. So we actually think it's a very good idea to just put in the whole page and develop an approach that is less hardware hungry. So how does our system work? I already told you the backbone is standard. We don't do anything special there. It's just a fully convolutional architecture. The specifics lie in the different output heads. And let's see how that looks like in practice. For oh, I'm sorry, I don't have a picture of how it looks for the human, the actual written music, but you can imagine every dot here is at the center of a musical symbol, so at the center of a note head, probably this will be, and here this is maybe the flag at the stem of the note. It's probably something like that. And this is the ground truth. So we have the 3 output heads. We have an energy peak at the center of at the location of every object. At the same position, we have a class, like a note head, a stem, a flag, and so on. And the bounding box parameters are encoded here in grayscale, which is difficult to interpret. Now, what does our detector detect then? You see here the detections for the energy, so where is an object, they are very, very, very accurate. That works amazingly well, very, very good. The class predictions look very artistically. You could print that out and put it on a wall as a poster. It looks very nice, but it doesn't seem to resemble the class ground truth very well. But that's actually not a problem, because all these larger colorful areas here, they give predictions for where the class energy tells us it's just background. So we can just ignore these large green area, for example, and look at, okay, at the respective dot, what should be the class for exactly that pixel. And that works, again, very, very well. The same for the bounding boxes. We don't care that the predictions for the background are off. We actually don't penalize it in the loss. We only care for that the bounding boxes and the class is to the point where we actually have an object. So how does it work in practice or in the industry with our partner? First, of course, we had to deal with a huge class imbalance, and the pragmatic solution we came up with, actually together with a PhD student that is about to graduate from Ca' Foscari University. I co-supervised him together with Marcello Pellino. And Ismail implemented that stuff. We actually augmented our data by putting randomly selected with equal probability symbols into the margins of each page, so that on average, after at least every 10th page, every symbol is seen again by the detector during training. And that works to very well regularize the training, so we don't have a huge imbalance problem anymore. And second, we did transfer learning to transfer from our perfectly produced PDFs to scans of the same things. We did some classic computer vision stuff, image processing stuff to realign the scans to our ground truth. So we didn't need to rely on hand annotations. And actually with that, we were able to improve the mean average precision from 16%. That was mainly due to, and it's a bad result, that was mainly due to the huge class imbalance. I mean, we detected all the notates probably perfectly, but all the rarer symbols not at all, and then the mean is bad. Using these and other tricks, we were able to improve that to 33%, which is amazing, we thought. And then shortly after, a guy from the Technical University of Vienna, not in relation to us, produced an overview paper on the state of the art in music object recognition, and found out that our work basically is 2 times better than the next competitor in optical music recognition.
Thilo?
Yeah.
Thilo, sorry, there is a question from Sinem.
Yes, please.
Sinem? Hello?
Oh, hello. Thank you for your presentation. So I have written on the chat screen, but I was curious, how many classes do you have in this problem?
It's about 130. So we were in long discussions with our industrial partner, basically which musical symbols to include, because I mean, there's a common set of maybe 70, 80 symbols that every musician probably knows. And then there's a long tail of symbols that only have been used centuries ago and so on. And we basically included most of them as well. So we come up with 130 different classes. I think this picture you should show you all of them.
Okay, thank you. What about how many training images have you used?
A lot of them actually. The actual number slipped my memory. It's in the paper. In this one here, the deep scores paper. That's the name of the open source data set. So the data set is really huge. I think it has 300,000 pages of music notation from real music, like not randomly assembled, but from, it's basically sourced from the largest music XML open source database on the web. We use that by permission. And every page has up to 1,000 different objects. Okay. So 300,000 pages, 1,000 objects, up to 1,000 objects per page.
Okay, thank you very much.
You're welcome.
So Maria also has a question for you.
Sure.
Yes, first of all, thank you for this presentation about these topics that are very interesting. I was wondering if this technology could also work with handwritten scores, because actually this could also be a truly important area for composers.
Yes, thanks for the question. we did one test at the when we were publishing this, so already 2 years ago, with handwritten music, and it worked amazingly well.
Yes.
It's probably hard to read on that slide, but the lower system here is from the Musima++ database, which is handwritten music. We haven't trained explicitly for that, so we were amazed that it worked, and I think it could work even better if we would put more training data into it.
Mm-hmm. Okay, thank you.
You're welcome. I would just continue. Is that okay?
Yes, please go on. Thank you.
Good. So, yeah, we were really happy with the results. Improving state of the art by a factor of 2 was actually pretty nice. And our project is still ongoing. Actually, we have the follow-up project just started roughly half a year ago. So there it's about moving from perfectly produced digital PDFs to musical scores from the wild.
Sorry, Thilo, before going to the next topic, there was a question by Sigrid.
Yeah, sure.
I think it's related to the previous example.
Sure, go ahead.
Please, Sigrid. Hello?
Yeah, sorry, it's John here. It's an aftermath of another Zoom session. I have the wrong name. So the question is just, with the number of symbols, it's much larger if you include the positioning of the notes with respect to the staff, obviously. And I'm just wondering about how you decompose the staff lines and the symbols of the note heads. What's the mechanism that you're using there? Like, how do you tell the difference between an A and a C? Just positionally? Do you dissect these as separate classes or what?
Just positionally, exactly. So we don't have to tell the system that's an A, that's a C. We just have to say that's a black note head at that and that position. And because the system that's collecting our information knows where the system is, where the lines are, the staff lines, the system then infers, that's an A and a C. In a new version, we actually give an additional information per node that we say, is it on a line or between the lines? Because that's often just a pixel or 2 difference. So this is now also given by our detector, but actually we only have a symbol black node head on a line and black node head between lines. We don't have all the different pitches, which makes it easier.
Okay, thank you.
You're welcome. Next steps in that project. So we're trying to transfer from our perfectly rendered PDFs to scans like what you see here, maybe done with a mobile phone, maybe done on scores that have been in the pocket of the musician for 10 years and they're a little bit like not in the best shape anymore. So we have to deal with noise and stuff like that. What we also try to do is get out real confidence measures from our detector. And you all know you probably cannot rely on the softmax probabilities for that. And we want to superimpose it like a heat map, like you see it in the lower left symbolic image here. We want to superimpose something like that on the picture that we're analyzing. So a human annotator can easily check where it's worth putting the effort of checking if every symbol was detected correctly. Because if you're doing that for professional musicians, if you do more than 1 mistake per page, you can basically do everything by hand again, and the whole approach is not usable anymore for an orchestra, for example. Just quickly, what we are currently working on is detecting bounding boxes at the right angle. You see it here with again a symbolic picture. When we have oriented bounding boxes and not just always upright, we can make them much more tight, and this gives us better estimate of the location of each symbol. And lastly, that goes a little bit into the area of Maria's question. We think that this approach is not specifically tailored to music recognition. It's tailored for detecting many tiny objects on large images. So what we're currently working on as well is transferring it to different domains, especially medical imaging, where you have huge resolution images, very small objects that need to be detected. And I'm awaiting first results in the next month. So this is it on optical music recognition. Achille, how much time should we still spend with the talk?
Oh, please go ahead. You know,
Okay.
we have 10 more minutes.
Oh, wonderful. That's perfect. So I go into the second use case. This one also was done in conjunction with industry. We were approached by a company from the Zurich area that is since over 140 years doing media monitoring of print media. Of course, in the past, completely manually. Basically, what they do is you can register there as a customer and say, every time a specific keyword or context is mentioned in the press, please drop me a note. It could be like, for example, our university pays for their service. Every time our university is mentioned in the press in Switzerland, we get the article cropped. But you could also, as a private investor, say, oh, I want to know when this and this person dies because of the death announcement, because I want to go to the ears and ask if I can buy their property that is at the Lake Zurich. Something like this is also possible, I have been told by the company. So what they do is every morning they get over 3,000 different newspapers from Switzerland and abroad, and they do a segmentation of every page into articles. And then they annotate automatically, of course, via OCR, the articles with all the keywords, and then the searches can go off automatically. But what cannot be done automatically so far is cutting out the articles from the page. So what you see here in the left picture is a page, whatever, some old German newspaper and German-speaking newspaper, and you see these blue crop marks around every article. And for us humans, it's super simple because we know the rules of layout, and we know that this picture probably does not belong to the tiny article to the left and so on. But for a computer vision approach, that was difficult. And we had a project where we tried two things, natural language processing, computer vision, and the combination of both to basically do this cutting of a page into the constituent articles. Of course, an image like the one to the left, such a page is super simple. Anyone could do that, even somebody who does not know the German language or even our letters. I would think if that would be Chinese, I could still do it because layout is universal. But if you look at the middle image of a more like boulevard kind of yellow press kind of newspaper, it's more ambiguous there. What actually belongs together? What is an article in itself? So that's a challenge. And really nasty is when you have a page full of these crossword riddles and stock market courses and weather forecasts. That doesn't work at all. So what we found out in that project is it doesn't work very well using NLP. Actually, NLP doesn't really add anything, natural language processing, looking at the text. It can actually be solved to a sufficient degree, sufficient for industrial application, using just computer vision, using deep neural networks. And what we are doing is, again, a fully convolutional neural network that gets as input two things. The whole page, really small, like I think it's less than 500 by 500 pixels. So the network looks at something similar that what you similar resolution that what you currently see here. And a second image goes in, a pre-processed one. This is basically the same page ran through a commercial OCR software, and then everywhere where the software detects either an image or a line of text, it is replaced just by a placeholder. So basically, the upper image here is a low resolution scan of the page, newspaper page, and the second image is every line of text that the OCR system that we take just from industry standard detects is replaced by a black bar, and every image is replaced by a frame. And these two things basically just stacked on each other as two channels, played through the neural network, put through the neural network, and the output should be a segmentation mask like what you see here to the right. Basically, everything that is a connected component and black is an article, and everywhere where you have white in between, these are the cut marks. And this can then be used by in a post-processing step to actually cut the articles out graphically. This system was quite successful. The company hired 3 of our students that went from the research side to the industrial side, that implemented the system into their pipeline. What you see here is basically what needs to be done for that system to be deployed. I mean, for us, it was interesting working 1.5-ish years on it to come up with a good approach. Interestingly, we came up with a good approach only with the very last idea. So 1.5 years, nothing worked. And then for the last 2 months, it worked. And then the same guys put a comparable amount of effort into it at the company side to basically put it into a process that can be automated, that can be run every day on hundreds of thousands of pages, and that is stable and that is robust against layout changes in the newspapers and so on. So our lessons learned from that project were twofold. From point of research, I think for industrial people, this is probably straightforward, but for us, it was like, oh yeah, processing speed is important. If you have to run that neural network on 100,000 of pages per day, and you have to be finished before 10 o'clock in the morning because everybody wants their like notifications for the board meetings and so on, processing speed is important. So we had to, basically the company re-implemented everything we gave them in, I think it was TensorFlow code. They re-implemented it in some way that was much quicker and improved it a lot in that respect, not in respect of accuracy, but in respect of robustness to crashes and software quality and so on. And then what is also important, I mean, we as researchers, we were finished when we achieved good results on our test set and we handed the prototype over to the company. Of course, they needed to implement something like continuous learning. Newspapers all the time evolve their layout. So all the time they have to retrain, they had to do a pipeline where they collect certain images that were misclassified, relabel them, put them into a training, update the model, and all this automatically, because you do not always want to have a specific person just looking for that. So it's quite interesting what still needs to be done when from a research side, we think, oh, we have a good running system and a very good solution. So to round off the talk, I will quickly give you an overview of other stuff apart from document recognition that we are working on. We just started actually together with Rudy, who's also in the talk, a project on improving the quality of CT scans using deep learning. There it's about removing artifacts and hopefully being able to get better scans from patients with a lower dose of radiation. Very interesting project, but results are still a way to go or so. Then I told you at the very beginning, we're also looking into reinforcement learning. We participated in a reinforcement learning challenge to optimize train rescheduling. And we just had a very good result in the respective competition, which will actually run a second time this year as an official workshop at NIPS and at NeurIPS. We also looked into, with another industrial partner from the consulting business, into automated machine learning and especially automated deep learning techniques, and had very, very good, usually top 5 results in the automated deep learning challenge that was run by Google and others during, which conference was it? During some conference beginning of that year. And finally, just to show the breadth of what you can do with computer vision, we are working to also with a semantic segmentation approach to reduce food waste by analyzing with a head-mounted camera what is put into the waste bin of an industrial kitchen in a restaurant or Mensa. And we are classifying basically what kind of waste is put in there. Is it meat or is it potatoes or is it only what is Schale? The skin of the potato, which of course should go into the waste. So that's also a currently running project. Conclusions. So in those settings in which we work, which are usually in conjunction with some industrial interest behind it, a couple of things are important. Sample efficiency. Usually we don't have a huge annotated benchmark data set like ImageNet. We have hand annotated data from the industrial partner, and every single image or audio file to get annotated is costly. So we need to be very sample efficient, need solutions that work on small data. Oh, by the way, this thing for the newspaper segmentation, it worked on only 500 annotated pages, the training, and a couple of thousand partially annotated pages. So very, very small data case for a deep learning approach, and no transfer learning applied. Sample efficiency is important. Robustness in every respect is important. Interpretability is important. Usually there is some boss in the company that says, yeah, we are now using AI, but I need to tell my customer how it works. So I need, for every decision the computer takes, I need to be able to judge it if it's correct or not. So interpretability is really important. And it's cool because that's also a very good research topic. What will we do in the future? I think there's something coming up on deep learning-based speaker diarization. We will use our new object detector on medical imaging and other domains, and to address the challenges of interpretability and robustness. I think future work in different projects will contribute to explainable deep learning, because that's just very important. And with that, I'd like to thank you that you invested the time for this meeting today.
Thank you very much, Thilo, for this very, very nice journey. I think it was fascinating. In fact, I have a couple of questions myself, but first I would like to see if there are questions from the audience. Yes, Tevodos, yes, please speak up.
Okay, thank you very much for this interesting presentation. And I'm wondering, in your works, what is the main motivation and criteria in choosing a specific deep learning architecture?
So for us as researchers, it's really just a matter of being competitive. When you're too broad, you cannot do anything deep. So as a research team, we said we have to be good in something. And deep learning is very interesting because there are so many things not yet explored, so many things that don't work yet, especially if you look at fresh cases. But of course, deep learning is by no way the most important or whatever a tool. There are a lot of things in pattern recognition you should and could do with different methods. So when we select a use case to become a project, we are looking for the things where we can actually do a contribution by furthering deep learning technology. So we are looking specifically at use cases where we think deep learning would be the way to go, so that we can continue what we started working on. And we give the cases where other methods should be used to our colleagues who are focusing on the other methods.
Okay, thank you.
You're welcome.
Okay, other questions? Well, I think John has another question. Please, John.
Okay, well, nice talk, Thilo. Thanks very much. I'm just curious about the visualization emphasis of your talk, which is sort of clear given the sort of intellectual background of doing this. But if you're analyzing music scores, it would seem to be appropriate to include the acoustic dimension and pattern recognition on sound as part of the procedure. And I'm just wondering whether you actually have any integration with acoustic checking or quality control or feedback in the process of using pattern recognition on the scores.
Thanks for the question. That would actually be very interesting. I would be delighted to work more on audio data. Much too much images nowadays for us. Actually, the use case of the company is works in a way that for the musical object recognition, there is no acoustic at that stage. They use our system in the following way. An orchestra or a conductor comes and says, here are our scores, like that we are going to play next month, hundreds of pages, please digitize them for us. And then they could do it manually at extreme high costs, or they put it through our system. And in the future, they are producing an app. customers could even do it with their smartphone, like our system is running in the background and you have musical scores in front of you, you put it on the table, take a picture, you see the see it calculating for a while, and then you get the result. So basically, the conversion from written music to digitized music is done while there is no audio. But there is one case where audio plays a role, and this is, I told you the whole idea is to have a digital music stand is to have convenience features like being able to transpose the music or being able to jump to a specific location, or for the conductor to change the page for all the orchestra at once. And one interesting thing, which of course doesn't make too much sense, what would make sense is if every digital music stand would listen to what the musician is currently playing, compare it to what is currently on the screen, and flip the page just in the right moment so that the musician can play the violin, the flute, the guitar, or whatever, and doesn't need a hand to flip the page. And this is actually done. We thought several times about putting it into the research project as well, but currently we're trying to tackle that with the students. So basically, when the optical music recognition is already finished, we still have an audio processing use case by basically aligning what is on the screen to what is in the microphone, trying to see where in the score are we, and then automatically flipping a page if that is appropriate.
Yeah, thanks for that. There's just one small follow-on question related to the whole idea of accuracy of musical exposition.
Mm-hmm.
So another use case potentially is verification of accurate score rendition. And for most of your database, I would imagine that there are musical scores available, so you could both check and evaluate your accuracy with respect to the musical scores, even in the absence of accurate digital data. Right?
That's a very good idea. Thank you. Yeah, I have to check that. Thank you.
Pleasure.
Okay. Wait, can I ask you, related questions? Imagine that you have access to the full, say, Schubert archive, which includes not only music scores but also letters, and other data, related to different, to his life. Would it be possible within your approach to combine your approach with other more standard artificial life approaches that typically they select them, they identify metadata in which something which is related, and then combine it with the music score to see whether there are emerging stories. Say Schubert that in a specific period of his life was writing music because it was something related to his life. Would that be possible?
I think so, because I guess those approaches need to operate on different levels. We are, so to say, on the very low level. We are going from pixel to object location. But to do what you mentioned, if I understood that correctly, that's much more on a semantic level, so much a higher level. So in order to do such higher level recognition of themes and comparisons of things, you would need at the lower level an approach like ours that is very good in detecting the symbols with high accuracy, so that the subsequent analysis makes sense. Yeah, of course, that would be a very good combination.
Well, I'm asking because we did a project on that. I mean, not on music, but on archive, historical archive, and that was giving us metadata, and from this metadata we could reconstruct stories.
Mm-hmm.
So you can combine this with, for example, network theory. Mm-hmm. And Raffaella Burioni was part of the audience. Now she's left, but she was part of the team. So in principle, we did this for historical archives. For the history of Venice, for example, you can identify stories, from the digitized metadata. So one possibility would be to do this also for combine this with musical scores, in which you do the same with emerging story of the composers, for example.
Yeah, very interesting. Yes, thank you.
Okay, other questions? Because I also have questions related to the medical part, this visual. Is it possible to, I think it would be useful for neuroscience, for example, or cognitive science, to identify, that in neuroscience, of course, they can measure a very clearly. They can identify the regions of the brain that are active, under some circumstances. And I was wondering whether you can add something to it, in the sense that again to reconstruct pattern recognition. So what are the regions of the brain which are active under specific conditions?
I'm not sure if that specific method would be of much help there. What we are currently doing is to use it on images like the sample image I had on that slide here. This one, to detect, for example, cancerous cells. But for the use case you're describing, one of my postdocs that recently joined our lab has a very good background in brain-computer interfaces, and has data like the one you described from a previously finished research project that is not much analyzed so far, and we will be having a student thesis in the next semester to find out how can artificial neural networks help find out something about the biological ones. I'm very much looking forward to that, but I don't think that this specific method will be of much use here. But
you never know. Yes.
we will see. It's research.
Okay. I don't see other questions. So let's thank the speaker, Thilo, again, for this very, very nice presentation. And I hope that you join us again next Friday, June the 10th. We will have a seminar by Gregor Schroeder from the University of Bochum, who is a new representative member of University of Bochum. Okay, thanks again, and I see you on July the 10th.
Thank you. Oh, does anybody need the slides? Shall I send them to somebody so they can be made available?
Please, yes, please send it to ECLT@uniweb.it to Alessandra, who is our
very good
driving force. So thank you. Yeah, that's the seminar is being recorded. Will be put on the YouTube, our channel on YouTube. But the slides will also be useful. Yes, thank you very much.
Good. Thanks everyone for listening. Goodbye.
Bye. Thank you.